Welcome back to Pike Mathematics. Hopefully, you've had a chance to play around a bit with Iota on our website at pikemathematics.org. My intent today is to discuss the trig functions within Iota. After doing our introductory video, I wanted to follow up with another video that discusses all the many functions and operators in Iota. However, after surveying all that there is to cover, I've decided to break that topic into a series of 4 videos. Today, I will talk about trigonometry. Future videos will discuss matrix operations. There will be another video on derivatives and vector calculus. And finally, a video to cover some of the basic operators and a variety of miscellaneous functions like the absolute value or the norm function. A lot of what I have to say today can be found in the Help tab on our website. If you haven't explored that yet, I would encourage you to do so. There's a lot of really good information in there. In fact, I think I'll just show you the Help tab right now. So I hit accept, and we're in. Okay, go right to the top, Help. So we have the basic help, and then we have a separate help section for graphing. Well, let's just look at the basic right now. It has a table of contents that's well organized, and everything's hyperlinked, so you can get to where you need to go quickly. So we're going to talk about trigonometry today. Iota has a complete catalog of all the trig functions, and I can show you that right now, actually, in the help tab. So if I go to predefined functions, there you go. We got a table with all of these functions have been programmed into Iota. And so if you want to use any of them, you have to type them in exactly as you see it here. So sine, parentheses, x, parentheses, or arc, cosine, parentheses, x, parentheses. That's how you actually use it and call those functions in the system. So I want to show you a couple examples. So to do that, I'm going to go ahead and open up a paper. We'll do some basic things. The sine of 90 degrees. What is that? It's 1. You may have noticed I wrote sine of 90 and then equals in return. I can also go equals sine of 90 and then just return it, and I'll get the same result. Basically, you have to use an equal sign. You can do it before the equation or after the equation and then hit return, but there has to be the equal sign there. So let's try a couple of basics. Cosine of 180 degrees is -1. Or the tangent of 45 degrees is 1. So you notice I'm working in degrees here. That's the default setting in Iota, but you can actually change that. And so I'm going to start another paper where we can work in radians. So I hit math. And so right now you can see it was degrees was checked. Now I'm going to switch it over to radians. And let's try this again. I'll go sine of at pi divided by 2. So pi divided by 2 radians, we get what? Sine of pi over 2 is 1. All right, a little bit about this. I did this at pi. Basically, Iota has a bunch of constants that we've programmed into it, and pi is one of those. You can call the constants by starting with the at sign and then the code for the constant. And you can see those constants here back at the help page. If you click on the hyperlink for predefined constants, you can see them all right here. So obviously we have pi, so if you want to call pi, you have to do at pi. If you want to do Euler's number, it would be at e. So you can see we've got quite a few constants already programmed in there. It's really easy to put a constant into Iota. So if you look at this list and see if there's something that you would like for us to add, just email us at support@pikemathematics.org and we'd be happy to add it. I'll go back to our paper. So we did sine of pi over 2. Let's do the cosine of pi. Still equal to -1. The tangent of pi divided by 4 is 1. Okay. And we don't have just sine, cosine, and tangent. We could also do secant of pi. That's equal to -1. So like I said, we've got all the trig functions programmed in there. I know I said I wouldn't talk derivatives today, but I could do this quickly. If I do \d_x, sine of x. That'll give us the derivative of sine x, which is cosine x. How about the derivative of tangent? Typically, you'd say it's derivative of tangent is secant squared, but iota puts everything back into the cosine, tangent, and sine. So 1 over cosine squared is the same thing as secant squared. So those are kind of the classic trig functions. We also have the hyperbolic functions in the system. Um, for example, let's just talk a little bit about the hyperbolic cosine function. The hyperbolic cosine function is equal to this. It is equal to e to the x plus e to the negative x. Oops, take that one out. All divided by 2. All right. So you look right here. This is the way you'll typically see hyperbolic cosine written. So let's think if we put, for example, 0 into this equation. So e to the x would become 1, e to the negative x would become 1. So 1 plus 1 is 2 divided by 2. So we should get 1 as our answer. So let's check that real quick. The hyperbolic cosine of 0 equals 1. Okay. We also have the derivatives for the hyperbolic functions programmed in. So backslash d underscore x of hyperbolic cosine is sine, hyperbolic sine of x. So unlike the derivative of cosine of x is negative sine of x, in the hyperbolic world, the derivative of hyperbolic cosine is just the hyperbolic sine function. I'm going to make a little more space to work on the next few. Okay, so we have the regular trig functions, hyperbolic. We also have inverse trig functions. And remember what an inverse function is. If you have a function and you put x into it and it spits out y, if you put y into that function's inverse, it should spit out x. So we're going to kind of test that. We have arc tangent of x. Well, we did an example earlier. We did that the tangent of pi over 4 was 1. So we're going to put 1 into the arctan function here. See what we get. All right, so we get 0.79. Well, what is 0.79, which should be pi over 4? Let's test that real quick. I'm going to do at pi divided by 4. What does that come out to? Yep, 0.79. All right, so it's an inverse. We put in 1 and we got pi over 4. We also have all the derivatives for the inverse trig functions programmed. So let's try backslash d underscore x of arc tan x. And that is 1 over x squared plus 1. Okay. Let's make a little more room. Okay. So we also have the inverse hyperbolic functions programmed in. And again, what is the inverse function? If you have the function and you put in x, it spits out y. If you put y into the inverse function, you should get x. And we will test that with arc hyperbolic cosine. So we did hyperbolic cosine up here. We put 0 in and we got 1. So let's put 1 into here and hopefully we get 0. We do. All right. And last but not least, we also have the derivatives for the inverse hyperbolic functions program. So backslash d underscore x of arc cosine is, there you go, 1 over the square root of x squared minus 1. Okay. Next thing I want to talk about is trigonometric identities. Iota has a number of identities programmed into it to help simplify results. So it gets a result and it looks through its trig functions, all its trig identities, and if there's a way it can simplify it, it does that to kind of give a clearer answer. So for example, probably the most famous one in trig is cosine squared plus sine squared equals 1. Cosine squared plus sine squared equals 1. What else? It knows that cosine is a odd function, so that, or rather, sorry, I'm saying that wrong. Cosine is an even function. So the cosine of negative x is equal to the cosine of x. Okay. What else? It also knows, here's another example, the cosine of x times the cosine of y minus the sine of x times the sine of y equals the cosine of x plus y. Okay. It also knows a number of hyperbolic uh, trig identities. So the hyperbolic cosine squared minus hyperbolic sine squared equals, it equals 1. Okay. Here's the last one I want to show you. The cosine theta. You know what? I should probably make this point. I put theta in there, and what I did was backslash THE, and then you get the theta symbol. We have all of the Greek letters programmed as well, and so backslash and then the first three letters of the Greek letter will get you that symbol. So the cosine of theta plus I, because iota understands the imaginary, sine theta equals, there it is, Euler's formula. Uh, in my opinion, one of the most elegant formulas out there in the world of math and physics. Cosine theta plus I sine theta equals E to the I theta. Let's see, what else? I would like to graph something quickly. And that is, I want to display something first. We have the sine of I. We know, here, I'll do the sine of x. The sine of x is equal to E to the ix minus E to the minus ix. And all of that divided by 2. Okay. So this is what sine x is equal to. If you put an imaginary number in as the into the function, so uh, if you put ix into it, this is what you get. You get I times e to the x minus e the minus x to the minus x, and then all that divided by 2. Okay. This equation right here, this real component of this imaginary, this real piece here, comes up so often in math and physics that it's been given its own name. And this is the hyperbolic sine function. There's could do a similar thing for hyperbolic cosine, but this e to the x minus e to the minus x over 2, that is hyperbolic sine of x. I'd like to graph that right now. So I'm going to insert graphic. Okay. Let's say insert function. And go to plot x. Say sine hyperbolic of x. Okay. Well, we'll label this. Okay. Let's test it. See what it does. There we go. I'm going to add that. And I'm going to put a grid on it so we can see it nicely. Okay. So that's the hyperbolic sine function. truthfully, I've worked a lot with cosine and sine, and uh, uh, I understand how they look graphically better than hyperbolic sine. So one thing I can, but I'm just not that familiar with hyperbolic sine and how it looks on a graph. One thing I could do is, now that I understand this is what hyperbolic sine is, you'll notice that if you were to go in the positive x direction, this number uh, essentially gets really, really small, and it stops kind of contributing much, and it approaches zero. So as x gets large, the hyperbolic sine function basically starts to approximate e to the x over 2. So let's graph e to the x over 2 just to see how it compares to the hyperbolic sine function. I'm going to use the exponential function. That divided by 2. And we'll make it blue. Let's see. There it is. So I'm going to append that. Okay. So look, as soon as x gets a little bigger, it basically follows that e to the x over 2 graph. Well, what about on the negative x side? So as if when x gets negative, this number starts to become really small, but this number would start to blow up, but it's a negative number. Okay, so it's going to start to approximate negative e to the x over 2. Let's graph that one. I got to do have to put a negative in there. I have to put a negative in there as well. And we'll make that one in yellow. Test it. Yep. So you can see as x gets larger in the negative direction, the hyperbolic sine function starts to follow very closely with negative e to the negative x over 2. So I hope you found that interesting. These are the capabilities that you'll find in Iota for trigonometry. I want to thank you for taking the time to watch today. I hope you enjoyed this discussion on trig and that you use these features in the future in Iota. Thank you so much.